Physical Chemistry with me. Today we're going to look at the ultraviolet and visible regions of the spectrum and see what can be done there. So remembering last time, the distance between two atoms, for example, in a stretching vibration varies. This is the distance r, this is the two atoms. If we take an ethene molecule, for example, we can measure the distance between the two carbons. It's varying all the time, and a vibrational transition would be here between the energy levels inside here. The atom, or one of the atoms, is moving further away from the other one in these bounds here. So if we generate the molecular orbitals for this molecule, for the same molecule, we can see that the single bond here will be made from this orbital here, from one carbon, and this orbital here from another carbon. This is one of the degenerate sp hybrids, these three here. As we can see, there are three of them, so that makes them sp2 hybrids, and the orbital left over is this p orbital, which forms a double bond. The double bond is here and here in a weird way, unlike how we draw it. It's on the outside of the single bond. And this would be the orbitals that we would generate from that. The bonding orbital, a single bond bonding orbital, and a single bond anti-bonding orbital, and the double bond bonding orbital here, and the double bond anti-bonding orbital on the outside. They're symmetrical. You can see they are similar in geometry to the orbitals that they started from, and that the bonding orbitals are in between the atoms and the anti-bonding orbitals are on the outside. And in energies, we can say the sp2 orbital that we start with and the p orbital that we start with are pretty much the same energy, but they, when they're added together to form a bond, the single bond, the sigma bond from the sp2 orbital, is very low in energy, particularly compared to its anti-bonding partner, that's up here, and the pi bond, that's the p, the double bond coming from this p orbital, is much less low in energy. We get less energy for the second bond, and its anti-bonding orbital is also not as high. So now I've labelled it pi star, which is the anti-bonding orbital, sigma star, which is the anti-bonding orbital for the single bond, and I've drawn in the transition that we would like to investigate first, which is exciting an electron from the double bond into its anti-bonding orbital. That would effectively break the bond, the second bond, but because there's still a single bond there, the molecule doesn't fly apart. That makes it practically simpler for us to start with. So converting this into the same diagram that we had before, we've got the vibrational bands in here. This is the molecule expanding and contracting. We excite it to another level, and I've drawn a second set of these at a higher energy level because we've excited our electron. However, because we've broken a bond, we have to do two things. First of all, we shift the distance, because if we have a single bond instead of a double bond, the bond length is longer, it's not as strong. The second bond holds the atoms closer together, and the depth here, the energy required to shake the molecule apart, because if we increase it in temperature up to here, the molecule is so excited it can fall apart, it can go to infinity distance, it's broken, that's the end of our molecule. The energy required from where we start, the ground level, to where we shake it apart is much lower in the excited state because we only have a single bond rather than a double bond. Now we have the same logic as last time, but it's even stronger this time. If we excite our molecule, we are moving an electron to a higher level. The electron is a wave and it's very light, so we can do that, but we can't just shift this carbon atom to a different place while we're doing that. So the rule with these diagrams is that only vertical arrows are allowed, or only vertical arrows are easy to do, and so in this case the most likely transition will be a vertical one, and it won't be from the ground state that we typically have here to the ground state of our excited atom, so the electronically excited state. We will have to go to one of the excited states of our molecule, because this molecule can't suddenly stretch and snap into position out here where the ground state is. the overlap between where this atom is and where this atom is, the distance between the two atoms. And in this state, the distance between the atoms is very small, and so it's very unlikely that we'll be able to do this. It's much more likely that we will do this transition instead. However, it requires more energy. If we take a normal strength bond or a normal chemical, we notice that it rarely shows ultraviolet or visible bands. So it's only unusual colored compounds that do. This is an example. This is the compound in turmeric, curcumin, and you can see that it's got a very large structure. It's got 2 rings in it, and what is important about this molecule is that it has a lot of double bonds that are all connected to each other. We can see they're all connected to each other because all of the carbons in the molecule plus these oxygens, they have sp2 carbons and 1 p orbital left over, and the p orbital is involved in double bonding. But because these double bonds can move around, or because these double bonds are not limited to just here, they can go in the other space as well, all of these carbon atoms, all of these electrons are in the same orbital, which makes the levels that they can jump between very much lower, and that allows it to absorb light of a lower energy and get into the visible region. This dye appears to be yellow or red depending on pH. So if we simplify our diagram a little bit, we generate a slightly different looking diagram without the energy curves in here. We've got the energy level of the electron in the orbital, which can jump from here in its ground state up to here, but for the reasons that we explained before, it can't usually get from the ground state to the ground state up here, not directly. It is usually going from the ground state, so the lowest vibrational level, to an excited vibrational level in its excited electronic state. This diagram looks slightly simpler, but that's because I'm now going to use the x-axis for another thing. However, first we're going to explain a difference. So if we measure a spectrum, we can pass light through a compound that we're interested in and see that it absorbs light in certain colors in the ultraviolet or visible wavelengths that tell us that it's got a large structure of double bonds maybe, or some other way of absorbing the light. But once our molecule has been excited by a photon of light, it now has to get back down again somehow. It can lose its vibrational levels by crashing into stuff, because all it's doing, trying to get in front of you, is moving like this, and it crashes into another molecule, and that can transfer some of the vibrational energy into heat energy in another molecule. But what it can't do is transfer back into the electronic state without somehow giving out the energy in a different form, and this would very often be, in this case, a photon of light. Because this arrow on our energy scale is longer than this arrow, it means that the color of light that's coming in is bluer than the color of light that's going out. We have seen this, or you have seen this, in normal life, so I'm going to go and find a piece for you. So to look at this effect in reality, we can get in the dark, and I can shine an ultraviolet light at this piece of paper. The piece of paper has got 2 blocks on it made with this highlighter pen, which contains a fluorescent dye, which will convert the light from your ultraviolet torch from short wavelength ultraviolet light to green. The paper will also change the color of the light. So let's make it dark. It's really hard to do it backwards. There it is. So that's my green part in ultraviolet. Now you can see that it is absorbing the ultraviolet light and giving out green light. It actually looks a whole lot better to my eye than it does to you. While we're here, I have another substance which you can't see at the moment because I'm not shining an ultraviolet light on it. Here is my ultraviolet light source, and I'll shine it on there. and there. When I move it away, you can see it glows afterwards. There's an afterglow. You sort of paint it on first, and you can see it glows afterwards. I have another one, so that is going for quite some time, fading out slowly. This is another one, which again you can't see until I draw on it. This one, ooh, it does actually work. This one, you can see it changing the color from ultraviolet into an orangey color, and when I move it away, it carries on for some time. It actually appears to be green in the afterglow, and it appears to be orange in normal light. So there it is, glowing. It goes away faster than the other one. Doesn't actually. The other one is still, they're actually glowing to me quite brightly, but you can't see them at all because of how cameras work badly. So my normal paper, my normal highlighter pen, is taking ultraviolet light in here and relaxing, giving out colored light, visible light here. That's our normal step. So what is happening in the other case? That is in normal vision, this strange powder here. To explain this, we might as well go straight to oxygen, which is a complicated case, but never mind, hey, you always have those. So in our normal oxygen molecules, we see a double bond, O, double bond O, but the orbital structure is very strange. We've got the sigma bond, which is the normal p orbital pointing towards the other oxygen, forming a single bond. This is here. But instead of having just one double bond on the outside, it has two double bonds at 90 degrees to each other, one here and one here. But that would make three bonds. That would be stupid, or it would be not what we see. So there are electrons in the antibonding orbitals as well, the pi antibonding orbitals, which are on the outside of the molecule, and they are in these two orbitals, and because they are two electrons, instead of going into the same orbital here, one goes into each and they point the same way. So looking at this molecule, the oxygen, the lowest energy thing that we could possibly do is turn that electron, this one here, upside down, flipping the electron over, and that is possible. However, it would require a unit of rotational angular momentum. So we see that oxygen is an interesting molecule. It has in its highest energy state, this one, the highest occupied molecular orbital, it has two electrons pointing in the same direction, which makes it special. That makes it magnetic, so it responds to a magnetic field in a special way. It also means that it can't react directly with other molecules, because these two electrons can't be shoved into the same orbital to attack something. And there is no orbital here, there's no space for two electrons to go in that are in opposite directions as they would normally be if they were a lone pair on some other group. So to make the oxygen more reactive, what we could do is flip one of these electrons over and shove it into the same orbital. That's the second most least energy thing that we could do to it. The lowest energy would be just to flip the electron and leave it in the same orbital. Those things, however, are difficult to do with light, because it would require effectively quantum mechanically changing spin. It requires from physics angular momentum, and angular momentum is something that light doesn't have very much of. It has some, but not enough to rotate this electron into the other direction. That means that the transition is, for an optical transition from light, is not allowed, quantum mechanically not allowed, which it doesn't mean it doesn't happen, it means it's unlikely. So it is difficult to flip this electron over. So for allowed transitions, the lowest transition would be taking this electron, which happens to be pointing in the other direction, and exciting it up to here. That would be on this diagram this transition here, for example, and then we would need to draw the other ones on in a different way so we can move across our x-axis. That's why this x-axis in this particular diagram is weird. So this axis is now representing a thing that is not spatial, and it's not got, we can't give it units. So for illustrative purposes I've just drawn some transitions on. These are not necessarily the real ones, but it illustrates my point. So if we take the ground state of oxygen, this is the ground state of oxygen with 2 electrons in the same direction in the antibonding orbital, antibonding orbitals, and 4 in the bonding orbitals, ignoring the sigma bond because that doesn't change. Exciting one of these up, that would be the normal transition which we can do with light, so that can happen. Then we can have the lowest possible energy transition where we flip 1 electron over, that's this one. Flipped from here, we have the next highest possibility where we shove these 2 electrons in the same orbital, that's slightly higher in energy, and we have the next highest energy possibility where we do this, but we also flip an electron, so it's slightly higher than this one. If we take this example, we can say it is possible to be in this system, and it's possible to be in this system, but light has difficulty doing this transfer. However, if it interacts with other molecules, it can gain some angular momentum. If it interacts with other orbitals, it can gain some angular momentum. So this transition can happen, but it usually doesn't happen at the same time. And in our example, we can, for example, excite with our ultraviolet to this excited state, then it can fluoresce by falling back down again, or it can lose energy and flip over to become this excited state of oxygen, which can then lose energy. That would also be fluorescence. But what it can't do very easily is lose energy here to get back to the ground state, which it would have to do, which would then takes a long time. That's called phosphorescence, and that is what happens in my colored powders. So now we've got this new and possibly confusing type of diagram. It's called a Jablonski diagram. It has the different spin states of the electrons on the x-axis in this case, and we have energy levels vertically, but because we've lost some information from the diagram that we had before with the energy wells, we can't very easily do all possible transitions. So for example, the 0 to 0 transition is very difficult to do with light because the atoms aren't in the same position. So we've lost a little bit of that information. However, we can draw more easily this other information on that tells us if we go from this state to the excited state, we can flip an electron over and go to another excited state, which can lose energy relatively easily and come back to this state, or it could go directly back here. So in our phosphorescent dye, which would be this one, the energy levels probably look much more like this, where we have an excitation, and it can either lose the energy directly, or it can switch to a different state. So one of the electrons can flip over in spin, and then it's kind of stuck there, and it's not allowed quantum mechanically to come back, which tells us again, quantum mechanics, it is unlikely to happen, which means it takes a very long time comparatively. So this is measured in femtoseconds, picoseconds, sometimes a bit longer. This transition can be much longer, can be measured in seconds in extreme cases. So in my case, this is a very long one. It takes maybe 20 seconds to decay. So to recap and add one tiny more thing, we have 3 possibilities here. We can excite it, and we will measure in a type of absorption spectrum where we lose light. That will be here, so we'll call that A for absorption spectroscopy, ultraviolet visible absorption spectroscopy. We would see this light missing. That's what we see when we see color of something, like this green. We see a color it's missing certain colors, it's absorbing certain colors of light. Typically at that point it will hit things and relax non-radiatively. We will get no light out because it will hit stuff and warm it up, so it will go down to the ground state. We remembering we typically can't go from the ground state to the ground state because they don't fit, so it has to go to a higher excited state. However, we don't see very much coming back out of that higher excited state because it usually hits something unless we're at very low pressure. So we hit something else, we come back down, same rules apply. It's difficult to get from the ground state to the ground state, so we have to go to an excited state again because they don't fit. So then we get less energy out. That's our fluorescence. And typical fluorescence would be ultraviolet to visible, but there are other types of fluorescent, from visible to infrared, or between different colors of visible light, and they're quite common. But obviously for us, because we can't see ultraviolet light with our eyes and because we can see visible light, that's a particularly noticeable one. So we see that transition, that's quick. Then it will again hit things and go back down to the ground state. The other thing that can happen is this arrow here where an electron flips over. We like to call that intersystem crossing. You'll forget that immediately, but that's what it's called. So it can intersystem cross, and an electron flips over. Once it's done that, it can't flip back very easily. It's quantum mechanically not allowed, and therefore this process, phosphorescence, is much slower. I think that'll do for today. Next time we will look at what we can do when we measure this, at what these spectra look like, and what these look like.